Hello, and in this video, we are going to be looking at special types of systems. Please give this video a like if you find it helpful, subscribe for more math help, drop a comment or a question below, and check out the other videos and playlists on the channel for whatever questions you might have in your math journey. Now, I wanted to start this lesson by going over what we've covered thus far as we've studied systems of equations. And the first and most foundational thing that we've looked at is what systems are and what we're looking for when we solve them. Far too many math students just try to memorize all the different kinds of problems and what they're supposed to do when they see those problems, rather than getting at what is a system. So a system is more than one equation containing more than one variable. And what are we looking for when we solve them? Well, we're looking for the value of those variables that will make all of the equations in the system true. So we know what they are, and when we are told solve them, what we're looking for. And then we've gone over how to solve systems by graphing, substitution, and adding. And those are the three main ways that we do it. The graphing is very visual. Substitution and adding work for more than two variables, which graphing begins to get a little bit limited there. And those are our bedrock ways of what do we do when we're faced with the system. And we've looked at application of systems to real world scenarios. And if you want to go back and check out that video, it's a little bit longer, but it includes the practice in the video where we look at some, I guess we could call them word problems, but word problems and application problems, there's overlap, because application problems involve words, but we want to really look at real world scenarios. So we looked at some of that. Now, in this lesson, we're going to look at some of the odd things that can happen and what they mean. So there's two main weird things that can happen when you solve systems, and we just want to cover both of those things. There's no practice set for this lesson because this isn't really something that you would want to practice on, but you need to know, hey, you might be solving a system and some weird things could happen. So for this one is sort of set up for substitution. So I guess we'll go in that direction. I'm not thrilled with those fractions there, but we have 4x plus 8y equals 12 and y equals -1/2 x plus 3/2. And I'm going to take that and substitute that in for y. And so we will have 4x plus 8, and then I'll go ahead and change the color up just so we can see the substitution there. So we're going to take out the y, and in place of the y, we're going to put that whole chunk of stuff there, and all of that is equal to 12. And now I have one equation with one variable, and so I can go ahead and solve it. So we'll need to distribute the 8 through. And again, not super thrilled with the fraction arithmetic. I'm going to come over here and set up a spot for the fraction arithmetic. So we're going to have a 4x, and then we need 8 times -1/2. So remember that is 8 over 1. So we'll multiply going straight across. So 8 times -1 is -8. 1 times 2 is 2, and -8 divided by 2 is -4. So this will be plus -4x, and then we'll need to do the 8 times 3/2, and same deal. It's 8 over 1 times 3 over 2. So 8 times 3 is 24, 1 times 2 is 2, and 24 divided by 2 is 12. So that came out kind of nice. And then combining our like terms, we see 4x plus -4x. Well, 4x plus -4x is 0, leaving me with 12 equals 12. And so that seems odd, okay? We weren't expecting that. We were expecting to solve this system and get x is equal to some kind of number, or y is equal to some kind of number, because that's what happened. That's what's happened every other time. And what I landed with is just this true statement. Now, if you think about it for a moment, essentially what this might mean is that this is true no matter what you plug in for x, your value for x. So if you look back at this equation right here, if I plugged in anything for x, okay, like I could plug in x is 0, x is 1, x is 2, it doesn't matter what I plug in for x, this is going to end up being a true statement regardless, which means that if you plug in a value for X, get the value for Y, that you could have essentially like an infinite number of pairs of X's and Y's. You could take, X is equal to 1, and we'll just do X is equal to 2, and X is equal to 3, and just keep going. And for every value of X, there would be a value of Y, and they would all make the system true. So that seems a little bit weird, but it does seem like that's what's happening here. So next thing we're going to do is take a look at the graphs. Okay, and I encourage my students to do that. You land with something a little bit weird. Let's go ahead and plug both of those equations into Desmos and take a peek at what the graphs look like. So if we end up with two lines that intersect, then we know something has gone wrong. So here's what the graphs look like, and you might be a little bit confused, but Desmos does color code your graphs, and you'll notice we have a green one and we have a purple one. But when I look at the graph here, the coordinate plane, I only see the purple one. And that's because you can actually see where I left my cursor in there when I screenshotted it. That's the live equation. And essentially what is happening there is these two graphs are on top of each other. So the green one is underneath the purple one, and you can't see it because it's underneath it. So essentially those two equations are actually the same line. Okay, so when we go to graph them, the two graphs are right on top of each other, meaning that any point that makes the purple graph true, okay, or purple equation true, would also make the green equation true because they're the same line. So if there's a point on the purple line, it would also be on the green line because they're actually sitting in the same spot. So what does that mean? It means that those two equations represent the same line. Okay, and we can see that when we graph them. And what it means is that there are infinite solutions. So every point on the line will make both equations true. So just so we can see that. So here's my green line, and you've got this infinite number of points that are on that green line that all make the green equation true. And the purple line was sitting right on top of it, which means that all of those points would also make the purple equation true. So they are the same line, and we have infinite solutions. Now, there is a little disclaimer there. It is not true that all points are solutions. So you want to be really careful. Infinite points is not the same thing as all points. So you can have now this gets a little bit weird, especially for Algebra 1. But it means any point that's not on the line is not a solution. So are there an infinite number of points on the line? Absolutely, there are an infinite number of points on the line, but not all of the points that exist are on the line. So for example, that point is not a solution. Okay, that point is not on the line. So you want to be really careful about how you say that. You want to say the infinite number of solutions, but you don't want to say all the points are solutions. Just as another similar thing, with the idea of infinite, if you look at your number line, and let's say you were to look at, we'll say, even numbers, okay? And you can, I hope, see that there are an infinite number of even numbers, okay? So we have 2, 4, 6, 8, 10, 12, and we can keep going on forever. And you say, well, what's the next even number? But not all numbers are even, because 3 is not an even number. So we don't want to confuse infinite with all. Okay, so we have an infinite number of solutions, but not all of them. So that's the first weird thing, odd little thing that might happen. Here's another odd thing. So this one, we have another system of equations here. And this one I think I'm going to solve with adding, I guess. I'm going to multiply the top equation. If I want to eliminate the y's here, I would need to get a -8. So I would need to multiply by -2. So -2 times -x would give me +2x. Then we'll have -8y equals -24. And then coming down here, we have negative 2x plus 8y equals negative 8. And then you'll see the weird thing that's going to happen. I wanted to eliminate the y's. That was kind of the thought process that I went through. And what you notice happens is I'm also eliminating the x's. So 2x plus negative 2x is 0. Negative 8y plus 8y is 0. I end up with 0 over there. And this is negative 32. And so this just dumps out this false statement. So the last one dumped out a true statement. This one is dumping out a false statement because I went to eliminate one variable and I ended up eliminating 2 of them. And like, yeah, that's not a true thing. So this is a false statement, and this would make us maybe think that there are no solutions, okay? So maybe there's no values of x and y that could possibly make both of these equations true. Let's go take a look at the graph, okay? So we get something kind of weird popping out of our algebra. Let's go see what the graph looks like. And in this case, you can see there are the 2 equations, and lo and behold, what you see there are 2 parallel lines. So anything that makes, let's use the blue here, anything that makes the red equation true, so all of the points that are on that red line that make it true, none of those points are on the black line because they are 2 totally different lines. There are no places where those lines intersect where there is a value of x and y that will make both of the equations true, because those lines never intersect. And so you see what happens there. So we end up with like the true statement for the first case and then this like false statement. So what does this mean? This means that these lines are parallel, which means that they do not intersect and that there are no solutions to the system. So that, and this one doesn't have like it's a little bit easier to see. Like there are no solutions. So typically at the Algebra 1 level, it would be acceptable for students to simply write no solutions, okay? But you might see it expressed as the empty set, okay? And so there's a couple symbols for the empty set. One is that it's like a O with a line through it or a 0 through a line through it. You might also see set brackets with nothing in them. And both of those are ways of saying there are no solutions. So the set of solutions is empty. Okay, and that is a bit more of an advanced way of expressing the idea that there's no solutions. Like basically the set of all the points that could be solutions, that set has nothing in it. It is empty. Okay, so a couple more things. How can you spot these special cases? So if an experienced person is going to look at this, and there's a couple things that I would notice that would tip me off very quickly to, ooh, I got something weird going on. Look for common factors in the original equations, especially in that first case. So if you've got 2 lines that are the same line, the only way that can happen is if one of the equations is a multiple of the other equation. And so in that first example, anybody who's really experienced at dealing with systems is going to look at that 4x plus 8y equals 12, and they are going to see that all of those have a common factor of 4. So it probably came from this equation right here, okay, where somebody multiplied through, they multiplied the equation by 4, and it kind of got disguised. But if you look at this and you look at the other equation, you can see the 1 and the 3 to get that into slope-intercept form. And essentially what I did when I wrote that problem is I don't want it to be obvious that it's the same equation, because obviously if I did something like this and said, hey, solve this system, okay, and I did that, you would look at it right away, I hope, and would say that's the same equation. So we kind of disguised it a little bit. We put one of them in slope-intercept form and then multiply another one by a common factor, and we just kind of make it a little bit less obvious that it is the same equation. So that's something to look for. You start seeing those common factors. You might want to divide those common factors out, like kind of get rid of that common factor, and that will simplify the problem. The other thing is with the parallel lines will have the same slope. And you'll be able to see that if you put them in slope-intercept form. So these were the 2 equations that you were given, if you were to put these into slope-intercept form, we would say add the x to both sides. So we get 4y equals x plus 12, and then divide everything by 4, and we get y is equal to, that'll be 1/4 x plus 3. And then if I do the same thing with this one, now this one, you also, if you look down below, you can also see the second one by dividing out the common factor. I'll show you what I mean by that in a moment. But we'll add the 2y. No, sorry, that's a 2x. Okay, add the 2x to both sides. So we get 8y equals 2x minus 8, and divide everything by 8. And 2 divided by 8 right there is 1/4 x minus 1. And you can see that they both have a slope of 1/4. Now, another way you might be able to see that is by dividing out that common factor. So if you have 2x plus 8y equals -8, you're like, I see a common factor of 2. Those are all even numbers. And you say, okay, I'm going to divide both sides by 2. Make sure I divide everything. -2 divided by 2 is -1. 8 divided by 2 is 4. And then we have -4. And if you look closely, the first equation was -x plus 4y equals 12. And the second one was -x plus 4y equals -4. Well, -x plus 4y, like that's the same thing on the left, but one of them is equal to 12 and the other is equal to -4. And it can, if it's equal to 12, it can't be equal to -4. Like it just, -x plus 4y, like regardless of what you put in for your x and your y, if you put the same numbers in on the left, you should get the same number out on the right. And so that's another little tip off there. So those are a couple things that you can do just to be alert to these special cases. Now, will you see these a lot when you, in your journey through algebra doing systems? Are you going to see a ton of these? Not really, no. Okay, most of the systems that you are going to solve, you are going to get an answer out for the x and the y. You're not going to see these a whole lot. When they come up, the first thing you might want to do is just double check your work or check them by graphing, because they're not very common. They get kind of mixed in here or there. Certainly, if you are seeing them come up for every single problem, unless it's a problem set where that is the thing that you're studying and looking for, that would be a little bit of a red flag. But a lot of times students will freak out when they are solving a system and they get something like 5 equals 5 or 0 equals 0 or 2 equals 3 or something that's just a true statement or a false statement, and the x's and y's seem to go away. And then just kind of double check it. Maybe hop onto Desmos, graph the original equations, see if you get the same line, see if you get a parallel line. That'll give you a little bit of confidence as to whether or not you're seeing one of these special cases. And that's it. So don't forget, like and subscribe for more math content. Drop a comment or a question below, and check out the other videos on systems, as well as some of the other playlists that we have on the channel. And I will see you in the next one.